All right. Let's pick up again. Examples 2, 3, and 4, and then we will wrap up chapter 3. So, example 2. Now we'll use the other side, not use, but flip to the other side of the equation, meaning we are given the current and we are asked to find the voltage. So capacitor this time is 2 microfarads and current is given. Capacitor current is given as 6 times E raised to minus 3000 T milliamps. Okay. So now we perform the integration, and this is where I'll talk about the limits. This is the standard equation for the capacitor voltage, 1 over C integral of I dt. Now, integration, to put it simply, is a summation. You are summing up, or basically we say area under the curve, right? You're summing up individual slices. Individual slices of the current is basically noted by dt. When you're summing up, you have to determine, or not, you have to define a starting point and an end point. Now, for both the capacitor and the inductor, when you're trying to sum up, what you're trying to do is you're summing up basically the entire energy that created that voltage or that current, right? And now I'm talking just in general terms of both inductor and capacitor. So let's go back to this slide, this one right here, where I talk about the integration. Now I'm using the capacitor as an example, but the same concept applies if we were trying to find the inductor current, right? Inductor current IL is the integral of the inductor voltage. So again, IL is 1 over L integral of the inductor voltage. So we'll talk about this right here. So the limits of the integration, you're summing up everything, the starting point and the end point, okay? Now the starting point here is listed as minus infinity. Minus infinity means at the beginning of time. Well, not really. It is simply all of the stored energy or all of the stored stored current. Okay, so you integrate the current to find all of the stored energy from the beginning. Now we don't know what the beginning is, so it basically just means the initial stored energy. And this T right here signifies the end point of analysis. End point of analysis. But we don't know what that endpoint is. For every specific example, every specific case, it is different. Hence, we use a variable time t. So far, so good. Any questions? Let's take a pause. Any questions at all? All of the stored energy. So far, so good. Okay. All right. So then we break it up into two time portions, minus infinity to 2,0, and then t0 to t. And t0, and you will see this t0 again and again and again throughout the rest of the course. T0 simply signifies it's basically, you know what, let me write it. T0 is time with a value of 0. Simply notes the beginning point of your analysis. Okay, that beginning point of analysis could be anything. It's the moment you applied the input. It could be a second portion of the input. It could be a third portion, doesn't really matter when. But we analyze a system between a certain time point, and the T0 would signify that point in time where you begin your analysis. As an example, let's say you have a machine or a system that is running 24/7, right? At 9 o'clock in the morning, you wish to know what the voltage of the current is at any point in that circuit. Then T0 would be 9 a.m. If you wish to look at, I don't know, like 11:50 at night to see what the system is doing, you begin your analysis at 11:50, then T0 in that case would be 11:50 p.m. Does that make sense? Right? So T0 is simply the moment in time where you begin your analysis. So when you have your limits as minus infinity to T0, so T has a value between minus infinity to T0, what it is that you're actually looking at? Well, you're looking at all the end time period, meaning we began our analysis at T0. Minus infinity is all of the time that was in the past. So what we are trying to look for is all of the stored energy that was present in that component at the moment we begin our analysis. And we have to add that into our equation to determine our voltage or current. So again, I'll repeat. The concept of minus infinity to T0 means it is in the past. And from there, we would like to find or determine all of the stored energy in the component. Okay. So again, we are splitting it up into two parts. One part is T0 to T. This is the current one or the present. And minus infinity to T0 is the past. And that is significant because we need to look at all of the stored energy in that component. And again, using the previous example I made, if you have a system you're trying to analyze at 9 a.m. or let's say 11:50 p.m., there might be some stored energy prior to 9 a.m. We don't care how long the system was running. The system could have been running for like 1 minute or 1 hour or 1 day or 1 year. We don't know, right? So minus infinity just signifies a very long time in the past. T0 is the absolute present. So in that example, all of the energy that was present at 9 a.m., we have to add it in. And that is noted by the voltage at T0. So for a capacitor, it would be noted as Vc of T0. For an inductor, it would be IL at T0. Okay. So this is our main equation, 1 over C integral of IC. And the limits are from 0 to T. That T is simply indicating that the quantity is a function of time. This is where it gets a little bit confusing. Okay. We change the variable from T to X. Okay. We change the variable from T to X to avoid any confusion. In the EE class, the book that we use, I think the author keeps time T variable exactly the same. And so T is used as the variable as well as the limit for the integration. Here, In this equation, we are simply change the variable from t to x. And the reason is because we want the final answer. We want the final answer as a function of time. Function of time t. Meaning we want the answer as v of t or I of t. Hence, we have the limits of the integration as t. So obviously, if you have the limits of integration as t, and you keep the variable also as t, it causes a little bit of confusion. Let's take a pause. Let me know if something doesn't make sense. Any questions from anyone? Did it all make sense? Hopefully. All right, let's go into examples 3 and 4. And here, we're going to introduce a topic called piecewise linear analysis. Okay, piecewise linear analysis. Now, question simply states, if capacitor is 5 microfarads, find the current. Okay, find the current. How many of you have heard of piecewise linear analysis in your own engineering fields, perhaps? Okay, so in electrical engineering, we use this a lot because we analyze a lot of non-linear devices. Okay, not in this class, but the rest of the electronics, diodes, transistors, FETs, MOSFETs, all of those are non-linear devices. And so what we do there is we would break up our analysis. We break up our analysis into different pieces, into different chunks. And each piece has a linear relationship with time. So here we are given the voltage for the capacitor in graphical form. Okay, we are given the voltage in graphical form. We cannot use any equation to directly describe this voltage. So what we're going to do is we are going to break this up into two parts, 0 to 6 and 6 to 8. Okay, 0 to 6 and 6 to 8. We are going to call time t1 as the period between 0 to 6 milliseconds. And between each time period, we can see the value of the voltage is linear with respect to time, meaning it is a straight line. And if it is a straight line, we can use the slope line intercept method to describe that line. You might be familiar with this expression, y is equal to mx plus b. You might be familiar with this, perhaps using different variables. Sometimes c is used instead of b, but the standard expression remains the same. The variable y is the voltage, right? Variable y is the voltage. M is the slope. X is time, and B is the y-intercept. And here's the beauty of this method to find the capacitor current. Capacitor current is given by IC dV over dt, rate of change of voltage. So let's find the slope. Slope M is y2 minus y1 divided by x2 minus x1. Any 2 points gives you the slope. Typically, I just use the 2 endpoints of the line. So for time period T1, we'll call this as M1. 24 minus 0 divided by 6 minus 0, 6 milliseconds. So you have to keep that in mind. It gives me 24 minus 0 divided by 6 into 10 is to E gives me 4,000. Right? So it'll be 4 volts per millisecond. 4 volts per millisecond. Let's take a pause. Write it down. Let me know if you have any questions. Do the steps make sense? Any questions? So now here's the beauty. What is the slope M of the line? We have this line. We found the slope. dV over dt. The slope of the line is telling us the rate at which the voltage changes, because T is on the x-axis, voltage V is on the y-axis. So it gives us dV over dt. So M1 or M is dV over dt. So if we wish to find the capacitor current, I'm going to say I1. It simply be M1 times, or C times M1. Five microfarads times 4 volts per millisecond gives me 20. If we didn't take care of the units, then our answer would turn out to be incorrect. 5 microfarads and 4 volts per millisecond. Or we could this also write down as 4,000 volts per second to keep everything straight. Okay, 4 volts per millisecond or 4,000 volts per second. So you get 20 milliamps. It is not a function of time, it's a constant value. Hence, when we plot it, it is simply a flat line, 20 milliamps. This is T1, this is for T2. Make sense? Similarly, for T2, time period T2 is between 6 milliseconds and 8 milliseconds. And my slope for this time period is T2 minus T1. Y2 minus Y1 divided by X2 minus X1. Taking the two endpoints, I get 0 minus 24 divided by 8 minus 6 into 10 raised to minus 3. And I get minus 12 volts per millisecond, or minus 12,000 volts per second. And therefore, I2 is C times M2, 5 into 10 raised to minus 6 into minus 12 divided by 1,000. And therefore, I2 is minus 60 milliamps, which is what we have here. All right, any questions? Let's take a pause while you write it all down. Let me know if you have any questions. The procedure makes sense? Any questions before I move on? Okay. Now, here's the thing about the integration that we're going to look at. So this is the flip side. We are given the current and we are asked to find the voltage. Okay, we're given the current, we're asked to find the voltage. So now what do we do? Okay. It's not quite clearly shown, but let me start off by stating that this value is 16. So this is 16 microamps. And this right here is minus 8. Okay. So the top peak is 16 microamps. The bottom is minus 8. Now, we proceed with the same manner. We are breaking it up. This is T1. This is T2. T1 is between 0 and 2 milliseconds. And T2 is between 2 and 4 milliseconds. This is the standard expression to determine the voltage from the current. Right, so we have VC of t is 1 over C integral of IC of t. Okay, shall we proceed? All right. So we have the mathematical expression, but we don't have a mathematical or a quantitative definition of the current. So again, we're going to use the slope line intercept method to describe each individual piece of the capacitor current as a straight line. So between T1, you can see the line has a slope. For T2, between 2 and 4 milliseconds, it's a flat line. So we will describe the portion for T2 first. And there's nothing else to actually do. It simply has one single value for that entire time period. So for the time period T2, IC of T simply has a value of minus 8 microamps. And that's all. We don't need to do anything else. And that is what you see here. Minus 8 microamps. So it's a flat line. That's great. It's a constant. This one here shows the time period T1, T2. And then if you want to, we can state that this is T3, but it does not matter because after that point, it is just equal to 0. Okay. Make sense? Right? So the only portion we have to worry about to describe is T1. So for T1, again, y equal to mx plus b. I'm going to use that to describe my line. I need to find the slope first. M1 would be 16 microamps minus 0 microamps divided by my x coordinates, which is 2 milliseconds and 0 milliseconds. And so I can write this as 8 into 10 raised to minus 3 amps per second. Right? It is climbing up at a rate of 8 microamps per second. 8 microamps per second. So I would say about here. Eight microamps per second. Sorry, 8 milliamp. It should be 8 milliamps. Sorry, 8 milliamps per second. 8 microamps per millisecond, because x-axis value is milliseconds. Right. So 8 milliamps per second, but 8 microamps per millisecond. Right. Because the x-axis is milliseconds. And here again is, I would like to point out, all of the information is not always stated in the statement. Okay, so we have to look at the diagram itself to extract the information. So if we don't notice this milliseconds right here, our answers would be incorrect. This is where companies like to point out, we'll always look for candidates who pay attention to details. And that is one of the things I like to point out during my classes, right? There are some information, this crucial, important information that is hidden inside this figure. Well, not hidden, but we have to look at every single thing. So microamps and milliseconds is kind of important. Okay, so we have that. Now we use y equal to mx plus b to describe the line. So y is equal to mx plus b. Y, of course, is current I. Slope is 8 into 10 raised to minus 3. X is t, and my y-intercept is 0. Okay, y-intercept is 0. And that is my equation of the line for T1. So now that we have a quantitative description, let's go ahead and perform our integration. So we are integrating means we wish to find this, the value of this time period, or value of the voltage in this time period, T1 and T2. Okay. This right here is the time period minus infinity to 0, which means the initial stored energy for T1. Does that make sense? V of t is broken up into two time periods. For T1, let's write this down. T1, we're analyzing for T1. For T1, the beginning of analysis, meaning time T0, is 0 milliseconds. What is the end point? What is the end point for T1? It is 2 milliseconds. Our job is to derive an expression, derive an equation that would describe the value of that voltage between 0 and 2 milliseconds. Okay, so beginning of my analysis is 0 milliseconds, end of my analysis is at 2 milliseconds. And this is very important. Here we state 0 to t. 0 to t. Okay, this 0 to t is indicating 0 and 2 milliseconds. Now, if we are beginning our analysis at 0 milliseconds, we have to add in all of the stored energy prior to 0 milliseconds. Is anything given to us? No, nothing is given to us. It does not state in the problem explicitly. There is no other way we can determine it. So if something like that occurs, then we assume that there is no energy stored. Because nothing is explicitly stated, and hence we can state voltage prior to time t equal to 0 is 0 volts. There was no energy present in the circuit, nothing is stated, and so we take it as 0 volts. Then all that remains is to plug in the values into this equation and solve. Okay, so that voltage, of course, 1 over C, C is given as, let's see, what was the value of C? 4 microfarads. 4 microfarads. And so we have 1 over 4 microfarads. Let's see. Ten raised to minus 6. Integral 0 to t of 8 milli. So that would come outside 8 into 10 raised to minus 3. Wait, 8 into 10 raised to minus 3. Oh, that's right. 8 into 10 raised to minus 3 t, and t becomes T becomes, you know what, let me write this again from the beginning. V is 1 over C, 0 to T, and this is 8 into 10 raised to minus 3 T dot dt, and C, of course, is 4 microfarads. V is 8 into 10 raised to minus 3. And I'm going to change this T to X. And 4 into 10 raised to minus 6. And so integration of X becomes X squared over 2 between 0 to T. Okay. And this gives me answer V1 as 10 cube times T squared volts. 10 cube times T squared volts. Let's take a pause while you write it down. Let me know if you have any questions about any of the steps. Does that make sense? Why we change it to X? I used to like keep it as it is, but then I would be faced with a lot of questions from students after class was done. Like, where did it? Why is it T? And then again, we come back to T. Well, the answer is, of course, that we want the final answer as a function of time. The limits of the integration are also time T, and hence we change the variable from T to X. X squared over 2, plug in T, and we get the answer for V1 as 10 cubed times T squared. All good? Okay, so now we go to the next time period. This equation is only valid for this first time period right here. Now we have to do this time T2. Okay, so this is T1, this is T2. Now for T2, for time period T2, what is the beginning point of our analysis? 2 milliseconds. So time T0 for the second time period is 2 milliseconds. And the end point of our analysis is 4 milliseconds. Is it starting to make more sense now? Right? Our beginning point of the analysis for T2 is 2 milliseconds. And this time we need to know what the initial stored energy is. So V of 0 for this time period, yes. Yeah, that's what we're doing. We can just, yeah, exactly. The question being asked is, can we just simply take the area under the curve? And that is exactly, yeah, right. We can just do that. Yep, that's what I, you know, at the beginning I said, this is what we're trying to find out. Yep. So again, you know, this goes back to like the first week I stated, right? There could be multiple ways to solve the same problem. So as engineers in real life, you could pick the most efficient, and most efficient in many cases would mean the quickest in terms of time or the cheapest in terms of money. You could also use multiple methods to verify your answers, right? In real life, we will not have a solutions manual. It will be our job as engineers to figure out whether our answers are correct or not. And so you could use multiple methods. So this would be an instance where we could do that. So let's do it the harder way, because you know we are required to teach the meaning of this initial stored energy. So V0 in this case would be the voltage present in the circuit at 2 milliseconds. Voltage at 2 milliseconds. And for that, we need to go prior time interval, which is here. And voltage at 2 milliseconds would be to t equals 2 milliseconds. And that would give us, well, that would give us this, 4 millivolts. 10 cube times t square. T is 2 milliseconds. You plug in the value of t in that equation, you solve it, and you obtain that voltage as 4 millivolts. This 4 millivolts is what we have to add, or what we must add to our equation for the second time period. Okay, let me go back to the slide if you're writing this down. V1 is 10 cubed times t squared. T is 2 milliseconds. We plug that into the equation and we solve this and we obtain 4 millivolts. Make sense? Okay. So we add that into our expression here. And this is V at time t equals 2 milliseconds. This becomes a little straightforward because we have a constant. So V of t is again 1 over c. So it's 1 over c integral 2 milliseconds and ending at t. And this would be a constant. So it is minus 8 microamps. Minus 8 microamps. Plus voltage at 2 milliseconds. And then you plug and solve. And we'd obtain minus 8 into 10 raised to minus 6 divided by 4 microfarads. 4 into 10 raised to minus 6. And from there, you obtain x 2 milliseconds and t plus 4 millivolts. Minus 2t minus 2t plus 8 into 10 raised to minus 3 and volts. Write it down. Let me know if you have any questions. Any questions? Do the steps make sense? All right, so in the old days, when we had to plot this, we would actually write out the steps. We would take the equation and we would plug in, like t equals 0.5, 1, 1.5, 2, and we would manually calculate manual calculation for every single point for voltage. Now, of course, you can simply plot this in MATLAB, any spreadsheet, anything you want, right? This is your time period 1. And this is time period T2. T1 has a curve because it was a function of T square, right? For time period T1, voltage was T square, whereas T2 was a function of T, so linear. Make sense? Any questions? Okay, so with that, we'll say is the conclusion of chapter 3. On Friday, we will begin and end chapter 4. Chapter 4 is looking at the energy transfer phase for the inductor and the capacitor. We will look at 4 different circuits. I will show the derivation for the voltage and the current for the capacitor and the inductor during the energy transfer, meaning receiving the energy and then sending the energy back into the circuit. At the end, we will see that there's one single equation that can suffice for the entire chapter. Okay, so we'll be able to finish everything on one day on Friday. And then the last 2 weeks, or the last 6, 7, 8, 10 classes would be devoted to AC analysis. Okay. All right, so we'll end class here today, and I will see you all on Friday for chapter 4. If you have any questions, I will be in my office this afternoon. All right, I'll bid you all a good